Hey guys, this is Sean Alexander with Alexander Math and Physics Tutoring, and today's topic is going to be conservation of momentum for my physics students. I personally love conservation of momentum because it's the only principle in physics that's known to never be violated at any scale. So they use conservation of momentum when they're colliding protons at the particle accelerator in Switzerland, and they use it for day-to-day size stuff like cars and billiard balls, and even on the galactic scale, it's always true. So let's take a quick look at a problem, and I just want to show you the best way to do it and the common mistake that students have. So step one, always and forever in a physics problem, is to draw a coordinate system. You can see my video on coordinate systems in the 8-step method. In this case, we're just going to be in one dimension. So I'm going to make ourselves an x-axis. Coordinate systems are so important because they define direction for us. Okay, and then at the origin, I'm going to have a car traveling at, say, 8 meters per second. And let's say that it has a mass of 1,000 kg, kilograms. Okay? And going the other direction, or actually, let's say it's going the same direction, we'll have a truck a much more massive truck. Let's say that it has a mass of 3,000 kilograms and that it's traveling in the same direction with a speed of 5 meters per second. So basically what's going to happen is eventually the car is going to catch up and smash into the back of the truck. And what we're going to say is that they're going to stick together and keep moving. Okay? And the question is going to be, what is the speed of the combined car and truck after they collided? Okay, so here's what conservation of momentum states. What we're going to do is first write down momentum. They use the letter P for momentum, don't ask me why, but it's equal to the mass times the velocity. Okay, and you can think of momentum as how hard it's going to be to change something's motion. So something with a lot of momentum, it's going to require a lot of force to change its speed or direction. So a great example that I like to use are those big tanker ships we see going through the San Francisco Bay. Those carry a lot of momentum. The reason is because their mass is enormous. In fact, if those things just cut the engine, they would continue to coast for something like 15 to 20 miles just based on their momentum. It takes a lot of force to slow them down. An example of something with less momentum would be, like a bicycle compared to the oil tanker, you know what I'm saying? So if you're riding a bicycle, the mass is much less, and it takes a lot less force to knock you over or slow you down. Okay, so the conservation of momentum says that the total momentum of the system, and here by system I mean the two objects, in this case the car and the truck, the total momentum of the car plus the truck cannot change. So whatever it was before the collision, it must be after the collision. And let's remember that momentum is a vector quantity, and so direction is important, okay? So total momentum before, so I'm going to say total P before equals total P, or momentum, after the collision. Okay, so what's the total momentum before? Well, what's the momentum of the car? Actually, in fact, the safest thing to do here is this. You're going to have, I'm going to call M1 the mass of the car times V1, the initial velocity of the car, plus M2 V2 initial, that's the mass and velocity of the truck, equals, the mass doesn't change, so that's going to call it M1, that's the mass of the car, times V1, the velocity of the car final, the velocity after the collision, plus M2, the mass of the truck, times the velocity of the truck final after the collision. Okay, so I would recommend starting, this would be your step 2. You can always just write this down right here for your conservation momentum problems. It's a very good starting point that'll keep you safe. And just the main problem that students run into is they don't consider direction. So it's very important that we consider direction. Okay, so let's just go through it. The mass of the car, M1, is 1,000 kg times the initial velocity of the car, which is 8 meters per second. Now here's where we need to consider sign. In this case, the 8 meters per second is positive because you can see that we've defined positive to be to the right. Okay, so we're going to use a positive number. If for any reason an object was going to the left, we would have to use a negative number. Okay, then we go, now we're here, plus we are now on this part here. So we're going to go M2, which is the mass of the truck, the bigger guy, times the velocity of the bigger guy. And again, we're going to use a positive quantity because the truck is moving in the positive x direction. If for any reason the truck was moving this way, which happens in a lot of problems too, you'd have to use a negative number. You would put negative 5 meters per second. But in this case, it's going in what we've defined as the positive x direction. So we're going to use a positive number. Okay? And we're going to set this equal, now we're on the right-hand side of the equation, to the final velocity. Now, M1 hasn't changed. That's the mass of the first car. That wouldn't change unless something broke off. V1 final, I'm just going to call V final now, because once the two things are stuck together, the car and the truck are going to be stuck together, moving together. So they're going to have the same final velocity. In other words, V1 final and V2 final are the same number because they're going to be stuck together, moving together. So we'll just call it V final. No need to differentiate. Okay, so plus M2, the mass of the truck, 3,000 kg, times same V final, again, because after the collision they're stuck together and they're going to have the same final velocity. Okay, now we just do the math. So for the first one, we have 1,000 times 8 is 8,000. Now we're a kilogram meter per second, which is the unit of momentum, plus 5 times 3,000, which is 15,000 kilograms meters per second. You can see our units are all the same, that of momentum. Now on the right-hand side, I'm noticing that there is a V final common to both terms. So if you recall from your algebra class, that means we can factor out the V final to get 1,000 kg plus 3,000 k, and then here is the V final, which we factored out. Okay, now let's just do some math. Going back to the left-hand side, 8,000 plus 15,000 is 23,000 kilogram meters per second equals 4,000 kilograms times V final. Now you'll notice that we can solve for V final. So we're going to divide both sides by 4,000, just using our algebra. 4,000 kilograms. And divide this side by 4 kilograms. So this cancels. And you'll notice the units work out too. This kilograms here cancels this kilograms here. And we are left with the proper unit, which is meters per second, because we're solving for a velocity, right? Okay, so then we just have 23 here. I can hack these zeros. Hack, hack, hack. And we get 23 divided by 4, which is 5.75 meters per second equals V final. Okay, and that's our final answer. We'll notice, now let's take a second to make sure our answer makes sense. We got a positive velocity, which implies that the combined truck and car are moving to the right. Does that make sense? Yes, that's what we expect, right? Once they crash together, since they're both started off going in the same direction, we expect them to speed off in the positive x direction, so that's good. And we got a magnitude of 5.75. Let's think about that. So the car is going at 8 meters per second, and it slams into the truck, which is going to be more difficult to move, going at 5 meters per second. So we expect the velocity of the combined car truck to increase, which it has. We got 5.75. You'll notice that it didn't increase that much. Why? Because the mass of the truck is so much greater. Anyway, that's an example of a conservation of momentum problem. I really hope that helps you out in your physics class. All right, guys, take care. Have a good one. Bye.